This is the notes for section 9.9, properties of logarithms. If you haven't done so already, make sure you stop the video at this time, read the section, and then continue on. I just want to briefly walk through the logarithmic theorems that were given to you presented to you in section 9.9. So I'm just going to quickly do that. It says log base b of b to the n theorem, and once again, if the base cannot be equal to 1, and any real number n, if that's the case, then log base b of b to the n is n, which makes sense if we think about that strictly from the standpoint of looking at it as a exponential form. The exponential form of that equation is b to the n equals b to the n. So that would make sense that that would be a true statement there. Next one, the log of 1 theorem for every positive base not equal to 1. The log base b of 1 is equal to 0. Well, that's just like saying if I think about it once again from an exponential standpoint, b to the 0 is equal to 1, which we know is a true statement. Okay, the product theorem and the quotient theorem are very similar to each other. Once again, b cannot be equal to 1, and x and y have to be positive real numbers. That's key, is that x and y have to be positive real numbers, and that applies for both for the product theorem and the quotient theorem. So what the product theorem says is if I have the log base b of the product of x and y, well then that's equal to the log base b of x plus the log base b of y. Okay? Now think about, you got to remember that x and y are like exponents in the exponential form. So we know if I have b to the x times b to the y, I'm going to add x and y together. So that's why that works. Now the same thing applies for the quotient theorem. If I have the log base b of x over y, in other words, I'm dividing x and y, well then another way of writing that is the log base b of x minus the log base b of y. And that's just like if you think about the exponential rules. If I have a quotient of two powered, the same base with different powers, I can subtract the powers in those quotients. Okay? And then the log of a power theorem just says if I have the log base b of x to the n, I can bring that n out in front of the log. So I can write it as n times the log base b of x. Okay? And then finally, the change of base theorem just says if I have the log base b of a, I can write that as the log of any base, log base anything, t we'll call it, of a over the log base t of b. So we can, that allows us to do is it allows us to change the base to one of our normal ones that we have a key on our calculator for. Now our cases are pretty well set up, so we don't have to use the change in base theorem as much as we used to with previous calculators, but it allows us to change the base to anything when we're looking at logs. So let's take a look at our first example here. It says find the log base 9 of 243 plus the log base 9 of 3 and check your results. Okay. So to do that, what I want to do is I want to go, okay, this, according to our log of product theorem, I know that this is the same as the log base 9 of 243 times 3, which is equal to the log base 9 of 729. Okay? And I know that 9 to some power is equal to 729. And that power would have to be, I've got to think about, well, what number can I raise 9 to and get that value? Well, if I do that, if I go 9 to the second, it's 81, and 9 to the third is 729. So n is equal to 3. Okay. Now, so let's just go to our calculator to check that then. And if we do that, if I put log base 9 of 243 plus the log base 9 of 3, you'll notice that I get an answer of 3 there. So it checks out that the answer should be 3. Number 2, let's take a look at that one. It says log base 6 of 48 we want to write that as the sum of two logarithms. The key to this one is that they want it as a sum of two logarithms. So the logarithmic property that allows us to write it as a sum is the product prop. You'll notice under the product property, I can take, and if I have two numbers multiplied together, I can split them up and write them as a sum. So what I want to think about is that number 48, and I want to think about how I could split 48 up into the product of two numbers, and then I'm going to split that up over here as logs and use it as a sum. So let's do that. So it says, so if I have the log base 6 of 48, I can say that's the same as the log base 6 of, well, let's think about numbers that evenly multiply together to get 48. So 6 times 8. Therefore, I can write that as the log base 6 of 6 plus the log base 6 of 8. There I'm writing it as the sum of two logs. We can kind of do the same thing because it asks us to do it twice. The log base 6 of 48 is equal to the log base 6 of 12 times 4. That also is 48. So I could write that as the log base 6 of 12 plus the log base 6 of 4. So I've written it in two different ways. So we can take a log and actually write it in a lot of different ways, using the product or the quotient, depending on how it sets up. Okay, number 3 says use the log of a quotient theorem to show that log base b of 1 over n is equal to negative log base b of n. Now there's more than one way that we can show that those are the same, but I want to do it using that quotient theorem. So what I'm going to do is I'm going to start with log base b of 1 over n, and I'm going to use the quotient theorem and keep working until I get to what I want it to look like. So using the quotient theorem, I can say this is the same as the log base b of 1 minus the log base b of n. Well, the log base b of 1 is 0. So I have 0 minus the log base b of n. Well, 0 minus the log base b of n is minus the log base b of n. And we've shown that those two things are equal. Alright, finally let's take a look at solving number 4 here. It asks us to solve this for d, and we need to use several properties in order to do that. So my goal, once again, is to figure out what d is. So let's do what we know. If I have a log base d of, now the first thing I'm going to deal with is this. Okay. Well, I know that I can do the following. I could bring the 3 up and put it as a power of 2. I'm using the log of a power theorem to do this, so if I know this is true, I can come back and write it like this, log base b of x to the n. Okay? So I'm going to write this as the log of 2 to the third power plus the log of 7 minus the log of 4. Okay? Finally, or I shouldn't say finally, next I'm going to take, I have 2 to the third, which is 8. So I have that's like saying the log of 8 plus the log of 7 minus the log of 4. Well, the log of 8 plus the log of 7, I can use the product theorem on that and say that that's the same as the log of 56 minus the log of 4. And then I can use the quotient theorem on that and say that's the same as the log of 56 divided by 4, which is equal to the log of 14. So I'm saying the log of d is equal to the log of 14. Well, I know that I want to know what d is. Well, if the log of d is equal to the log of 14, d must be equal to 14.